where we talk about how to choose the right NoSQL database.
So the general objectives, right? So what we are actually going to talk about today is what is the traditional databases, what are the general challenges that you face with traditional databases with the increase in the volume of data, and how do we manage things with them, what are the options available, and then finally we'll sort of see what comes to the rescue, NoSQL to the rescue. We'll talk about CAP Theorem, which is a pretty famous, sort of told by Brewer, which basically says that you have to forego one of the property to get the other two properties at the highest, best possible way. A base system, which is what is your NoSQL basic. Every NoSQL system is called a base system. Why and what, we will look at it. And then we will look at basically the most popular ones, the three popular NoSQL databases that's out there in the market and being used. So we'll look at what are how they are actually, what is their internal structure, and how do you choose between them when you have, depending upon your requirements. So that sort of is the objectives for today's session. So looking at the general database categories, right? So we have traditionally the storage systems could be broken down into multiple categories. One, surely we all know that it's RDBMS, which is the traditional RDBMS systems, which has been like relational systems, which have been there for many years, and something which we've been using across our throughout our life cycle, rather, sort of thing, I would say, as a software engineer, all along till now. Then you have the OLTP, which is the online transaction processing systems, which are also another pretty much in line with the RDBMS systems to some extent. And then you have the second category is basically, you can see the examples majorly are Oracle, MySQL, the Microsoft SQL, and then your DB2 sort of fall into this category. Then the second one are basically the OLAP kind of systems, which are more of online analytics processing systems. So are the data warehouse systems. So if you look at them, some basic examples would be SAP, HANA, Oracle Express, Netezza, all actually fall into this category. So the third set one, which is what the NoSQL or the new SQL, or rather the big data systems. So what is the difference? So basically, when you look at the traditional systems, right? So they have some shortcomings with respect to managing high data, because they put a lot of onus on the application to actually manage the distribution behind the scenes, because of which they have the shortcoming of, which sort of puts a lot of overhead and as well as degrade in their performance when they're managing ever-increasing data and managing huge volumes of data. That's where NoSQL actually comes into the picture to some extent. Okay, and then okay, one second, let's get to the next one. Okay, the examples of NoSQL are basically the Mongo, HBase, Couch, Cassandra are the set of things which are very popular in the NoSQL landscape. Okay, so looking at a simple application, a traditional, what do you call it? Basically a travel-based application. So if you're actually doing a travel booking site, you could actually go and then example could be the world's famous Expedia. So for example, if you take Expedia as an example, and then we go and search for a set of flights from one destination to another destination, source your destination in that place. So what you look at this kind of an application, the scale is probably the primary important factor, because you would be able to book tickets across the cities of the world, which are in thousands, and they are talking about if you're doing a hotel booking or a flight from one place to another place, there will be multiple flights for the same combination of source and destination. So if you look at these kind of a situation where you have hundreds of cities, millions of hotels, and hundreds of tens of combinations of a flight from one destination to another destination, and different types of flight providers or the service providers. So if you look at these kind of data, it's like pretty huge. The scale of the data is very, very huge. And then you're talking about so many people interacting with this kind of application, which is like approximately of the order of 5,000 TPS, 5,000 transactions per second, which could finally result in some sort of approximately 300 to 500 SQL transactions simultaneously. So if you want to scale your RDBMS to such kind of a level, what you would do basically is, your general basic RDBMS system, which you would set up on your, say, one of your in your local systems will not even suffice or will not even be able to handle so many simultaneous SQL transactions at any time. So you would have to scale your system either horizontally or vertically. So generally in the RDBMS world, we've always been trying to do vertical scaling. Basically, you're trying to add more resources to your existing system, existing server or the database server. For example, you try to up your overall memory capability of your system or increase your CPU capability of the system, add more cores to it, take a higher, better performance server. In all these cases, what you look for is the web application is sort of disrupted. Whenever you do any sort of scaling, vertical scaling, you want to scale your RDBMS, say, increase it by the CPU, or you want to add more memory, you have to bring down the application, add your resources, or rather increase the size of your server, vertically scale your server, and then the web application can be brought up again to serve the requests. So there is a disruption of application when you're using a vertical scaling methodology in the RDBMS world. Even in the case of horizontal scaling, where I could add more nodes in the RDBMS world, the problem happens is you end up actually sharding the table information. So when you do when you create shards, there is an additional onus on the web application, which is using the data, is to manage those shards. How do I actually aggregate data across those shards? How do I actually service the, answer the queries of the customer, answer the queries of the client, and etc. So those are some of the cases where it puts an onus on the web application to change, which is also another level of disruption. So whether you scale a RDBMS system horizontally or vertically, there is an absolute disruption with respect to the application. And if you look at a basic time series kind of an application, which is your travel portals, the need for writing data, changing data continuously is very, very high. I should be able to edit the price information on a regular basis. I should be able to run specialized promotions, because of which I have to provide prices at a different rate and things on those lines. So there is a lot of changing data that happens in these kind of applications. So there is a huge amount of writes that are happening, which is updating the data at the same time, and there's a huge amount of reads which are happening because of the loads of approximately 5,000 TPS of data, 5,000 transactions per second. So as a result of which, the overall read performance absolutely goes down, because your writes are very high, and all writes actually have some sort of locking mechanism in the RDBMS world. So in order to improve your read performance to some extent, there is an augmentation that you could provide, is by adding a caching layer in between. So if you add a caching layer, your read performance somewhat goes up, but still the application has the onus of managing the multiple shards, a capability to, naturally every horizontal scaling actually means a disruption to the web application. So these are the biggest problems that you would face in a RDBMS application. Now coming to a NoSQL database solution, right? So if you go to a NoSQL database solution, it provides you a capability, what we call it as elastic scale, which means, at least when it comes to Cassandra, you use Cassandra, it provides you a feature called elastic scalability, which automatically means that you could scale your basic base storage system absolutely independent and agnostic to your web application. So your web application doesn't have any disruption or any indication of what is the total number of nodes below in the storage subsystem which is servicing my client requests. So that way it just can scale very comfortably. So today it's 5,000 TPS. If it becomes 50,000 TPS, also you could add more nodes in your Cassandra cluster, and automatically the web application can serve it. Provided the web application has a capability to serve so many simultaneous requests, it can comfortably serve without any disruption. So that kind of a thing is something which is provided out of the box by NoSQL systems, because they provide you special properties called elastic scalability, at least in Cassandra. Okay, so what are the general challenges that we talked about? Sorry. Okay. So not a good for large data volumes, absolutely, because with varying data requirements, because if you look at the basic travel portal, there is too much of varying data requirements. And a couple of other scenarios which I could mention is, say in case if you want to add new hotels, or you want to add more features to an existing hotel, which means your the hotel table, or the one which actually has the hotel details information, has to have a constant changing capability, where I should be able to add more properties into it, which means my schema has to be varied. So you have varied data requirements. So schema has to be changing continuously. If you do the same thing in RDBMS world, schema changes is absolutely painful. People who are already worked with it should be, very, very familiar to changing a schema in RDBMS world. And again, one more level of disruption, you would call it as an application. So naturally, the RDBMS can scale beyond 50 to 20 petabytes of data, which is a pretty good example is our Aadhaar project, where we are really suffering because of that issue. Absolutely, vertical scaling could be always limited by memory and processing capabilities, which cannot go beyond a point. It has to have, there is a limit for that, how much we can increase and how much is available today as a prepackaged server, but not you can just increase it as if you like. So that's not going to happen. And then automatically there is a cost factor associated with it. So that would be one problem. Scaling up vertically is very, very tough. Okay, in the RDBMS is an issue anyways. So scale out automatically have issues with respect to your overall read-write performance. Plus, it has a problem. It has put on the onus of the application to manage those shards. And naturally, over a period, it becomes complex because more and more information means more and more parallel processing, then specialized layers which manages those shards and etc. in between. Okay, so that is automatically becomes a big failure in the RDBMS world. Consistency is something which is provided, but at the same time it actually creates a problem with respect to scalability. Satisfying ACID is surely a hindrance for scaling, because that's a very important requirement that's sitting out there in the RDBMS world, providing the ACID properties. It's automatically an hindrance to the scaling model. So you cannot just scale very easily because of the ACID properties that are to be satisfied in the RDBMS world. In the case of NoSQL databases, the only difference is your consistency is relaxed, which means because of which your scaling automatically becomes very easy when it comes to the scale out of NoSQL databases. Yes, there are several other properties which you could get out of the box, but we can talk about them in detail going forward. Okay, so let's understand what CAP Theorem means. The reason why we brought in CAP Theorem here is basically you need to understand how you want to compromise on one of them to get the other two, because there are basically three requirements which exist in the in the storage world to some extent, right? In any distributed architecture, storage applications kind of thing. Consistency, which means that your data in the database absolutely is consistent for every read. So every time a client reads a data, all clients get the same data. That is the consistency model. So then there is availability. Every time, every time a client makes a request, absolutely the service is always available and there is absolutely no downtime. Then comes to partition tolerance. Partition tolerance talks about mostly the scaling part of it. How do we actually scale the information and be able to distribute it across multiple groups very easily? Can be partitioned into multiple groups that can communicate with one another. Okay, so that's a partition tolerance concept. So there are three different concepts that we're talking about in CAP Theorem. What does the CAP Theorem say? It says basically I can achieve only two of them out of the three requirements. Okay, so it cannot achieve all three of them. In theory, it's absolutely impossible. It's absolutely impossible with all three requirements. But there are a few systems which could sort of go close, but they will come at the cost of some other parameters. So that's the important part which we need to understand. So if you are trying to adjust or have a capability in your system to adjust to the third factor, it comes at the cost of something additional to it. So for example, we'll talk about it in detail. First, let's understand the CAP theorem. So three things that you're talking about is consistency, availability, and partition tolerance. So if you look at the traditional RDBMS or the relational database systems, they sort of fall into the consistency and availability quadrant, which means they provide highly consistent data because every write actually happens on the database system in such a way that it's properly committed, and once it is committed, only then it's available for read for the rest of the people. So all your reads will sort of result in exactly the same result. So I said consistency and availability. Availability is achieved by most of the RDBMS systems like real application clusters, where you could run multiple parallel instances at the same time, which even if one instance or one of your database instance dies, the other database instance is available for you to service the requests of the customers. So that is what is achieved by using real application clusters, etc., which is pretty famous in the Oracle RAC and etc. So consistency or availability are achieved, but when it comes to partition tolerance, that is when you create shards, when you partition your database into multiple pieces, the RDBMS puts an onus on the application to make sure that you manage those shards. or you have to write a layer which will sort of manage those shards and service the requests of the customers. So that's why RDBMS is actually fails on the partition tolerance part of it, which is basically scaling. Partition tolerance is nothing but scaling horizontally, where you could add more nodes to accommodate for the increase of your overall data that's coming into your storage subsystem. So then coming to the second part, second quadrant, which is the consistency and the partition tolerance, where you're talking about the data is consistent, but your subsystem can scale very consistently, easily without much disruptions to the application. But it has a problem with respect to availability. See, consistency is again a factor where you need more control, right? So in the case of MongoDB, HBase, and Redis, which sort of fall into this category, they have this master-slave kind of a model. Because of this master-slave model, there is a lot of control in the way you write your data or read your data, which automatically guarantees consistency. But when it comes to partitioning, also they are very easily, because their base storage subsystem is either distributed into blocks or some sort of a column-oriented database, which helps in comfortable scaling. You can keep on adding more nodes and it will work comfortably. But they actually fall back on the availability part of it because of the master-slave model. Since if the master is not available, whether master is a single system or a set of systems, they have actually gone over it to some extent by using multiple systems as the master, where you have some sort of an availability at the master level. But even if it's a primary, secondary, master concept, at some point still it's a group of servers. So this group, if it's not available, the system still lacks availability issue. All your slaves are absolutely useless without the masters, without the group of masters. So that is where the Mongo and HBase sort of forego the availability to achieve consistency and partition tolerance. Now coming to the third quadrant, where you're talking about availability and partition tolerance, but lacking consistency. So if you look at the time series application which we talked about, consistency is not of primary importance to me there. For those kind of applications, I will choose this kind of storage subsystems which are falling in the availability and partition tolerance. Partition tolerance is basically I can scale very easily, absolutely without any problems. CouchDB, Cassandra, Dynamo, React, all these things actually fall into this quadrant, where they are eventually consistent models. They don't really are consistent all the time, which means if I have 3 or 4 clients making query for the same key or the same kind of same data, they might actually see different states of the same data, which means they might end up getting different values because of eventual consistency and not a strong consistency model. The only, if you look at, I think out of all set of things that I have worked with or rather have come across, there are only a couple of systems which sort of provide you a capability of adjustable consistency. Cassandra is one of them, and I think the other one is Voldemort. I've not completely used Voldemort in practice, but Cassandra provides you a capability of what we call it as a strong tunable consistency model. So it's probably the only system which, out of all the stuff which I know, which could sort of get it a little bit of entry to the third quadrant, but at the cost of performance. So if I make my consistency a strong consistency, absolutely the performance is worse than any of the RDBMS also. So this is not a ideal system for strong consistency based applications, where you need consistency is very important. You should not use these kind of storage subsystems. So this is what is the CAP Theorem. So you can achieve only 2 of them at the cost of the third one. There is no subsystem which is available, storage subsystem available, which can actually achieve all 3 of these parameters at the same time with the best of in an efficient manner. Okay. Consistency is not important in time series, because if you're looking at, say, I'm sure people would have used all these travel applications, right? When you use a travel application, you're first going and searching for your flights. At that time, you're not really bothered too much about the price to start with. Say, consistency of the price. What I would look for is what is the lowest possible available option. Say, for example, you got a Jet Airways flight, for example, going back to that one, Bangalore to Delhi, and Jet Airways says it's like, 5,000, whereas the other people say 6,000, so you'll probably choose Jet Airways. But if 5,000 actually becomes 5,100 or 4,900, you wouldn't really bother at the time of buying. It could change a little bit because of the consistency issues, but that is not really a problem, and this is something which is pretty common in all the travel booking sites when we have booked our tickets, right? So that's not really a problem when you're browsing, but once you book it, then things can't change, right? Once you do a booking with respect to either your seat has to be consistent. Your price has to be, which is allocated price has to be consistent. But before booking, all these things can change, because you might end up getting an offer. Say, for example, they want to reduce their flight charges on weekdays, right? That could be one of the options available. So that could be another offer which the travel company would provide, in which case your price will automatically go down for Monday, but it goes up for Sunday. Example cases. So also variation in price is not a very important thing, because the data actually changes with time. It's a time series data which changes with time. So consistency is not that important. So that's the reason the systems which are actually falling into the available and availability partition quadrant are more useful in the case where consistent, or rather give more efficient performance, perform more efficiently, or rather do your work much more efficiently in the case where consistency is not of high importance. So now, how does NoSQL come to the rescue? I mean, as I said, scale out, shared nothing architecture. Absolutely, there's nothing shared, because we're talking about distributed across data which is absolutely independent. Each node is independent of each other, and they're absolutely equal to each other. And the entire data is distributed into pieces and spread across this entire set of nodes which are there in the cluster. So shared nothing architecture, absolutely scale out, completely horizontal scaling, non-locking concurrency control mechanisms, because very beautiful system which I can actually talk more about Cassandra, because I've worked a lot in that practically compared to the rest of the ones. But example would be like all the writes in Cassandra are not really are not really the same model of any other write in the RDBMS world. So if you want to do a write in RDBMS world, you basically do a seek first to a particular key, and then do an update on that particular object, and then write it back to the database. Whereas you basically do 3-step process. But when it comes to Cassandra, it's just a 1-step process. I don't really bother about what is existing, I'll just go write. The eventual syncing and making sure what is valid, what is not valid happens behind the scenes. So that things actually scale your writes becomes very fast in Cassandra. So automatically your write speed goes up drastically. Scalable replication and distribution, because you can, since you can scale automatically by adding nodes without any application disruption, you can just keep on adding more and more machines to your cluster. And most often than not, the distribution is automatic in Cassandra, unless the administrator really wants to control it manually. So because your redistribution and everything actually works automatically, it's very easy to scale all this stuff. You don't really have to just go add a new node, and then the cluster adjusts automatically and then distributes your key space so that the new system can actually serve your requests. Okay. Naturally, which it provides a very high per node performance compared to any other SQL databases. As I said, because one of the performance-wise, it's basically the write and read latencies, right? The write latency is absolutely minimal in SQL because of the 1-step process, as I told you. And then read naturally is much faster, is much higher, even the read speed, because you're talking about say 10 entities doing the same job of one entity here. I have 10 commodity hardware servers sitting in the cluster, so all 10 can respond to queries at the same time. Since all nodes are absolutely equal, since there is no master-slave concept, there no centralized routing that's going to happen. You can just get very high and read and write speeds comparatively. Okay. Schema-less data model, which helps you to have sparse data models, which can say, like, if some particular system doesn't need a specific column, they need not have it, absolutely fine. And then somebody needs 10 other columns, they can actually add it up absolutely, and still everything could be stored in one place. The entire data model is denormalized. It's not really, absolutely not relational. So, and it's schema-less, so that you can add, have varied columns for a specific row. You can say in general terminology, I can have a table with rows having varied number of columns. And then you can dynamically add columns as and when needed, because just a similar case I said, right? If you want to add more properties to a hotel, I have a hotel today, I have probably provide only a shower, and so probably a shower, I mean, basic facilities, right? You want a television, you want audio system, and etc. which are in place. Now you want to add specialized spa facilities within the room, for example, is an additional facility that you want to advertise for your hotel, which will help probably people to choose the right kind of a hotel, in which case you should have a capability to add a new column which provides this property to the hotel. So you should be able to add dynamically a column to the data model, which is provided only by the NoSQL systems. But in the adding a new column, altering the existing schema in RDBMS is painful, and you all know why, because of the previously existing data, depopulating all nulls or something for that particular column, etc. And those are huge amount of problems that you would see in the NoSQL in the RDBMS world. Okay, mostly query and most of them are query stuff. So as I said, if you're looking at the travel portal, when you're searching, you are mostly querying, right? And updates will be there, which are specific to the set of data that's already there, and you're increasing the prices or changing the prices. That's where your updates come in picture. Okay, all these systems are basically, if you look at the travel portal, all these things hold good. It needs a schema-less data model because it can change as and when you need. It'll be mostly a query subsystem where you're doing a lot of queries and very less, comparatively less updates, but updates are always there. And then it's it has to be scalable. It has to be just keep on increasing, growing more and more and more and more data, because you have come up with new hotels, you come up with new cities which need to be registered into your travel portal and etc. Okay. So what does the NoSQL system database actually follow? They follow something called a base, but not an ACID system. Base, what does basic mean? Base means basically available. BA actually stands for basically available. The system does guarantee a complete availability in line with the CAP theorem, but naturally it gives up consistency, gives up on the consistency to make it available. Soft state indicates that the state of the system may change over time, which is what we call as a time series kind of a data which changes with time, and it provides you something called an eventual consistency. So if I have, say, 3 replicas within my storage subsystem, all 3 replicas are absolutely not in sync. They get in sync over a period. If you take an example of Cassandra again here, say if I have 3 replicas in a multi-data center deployment, the syncing of the replicas will actually have an additional parameter of the data center latency, right? So it has basically the data center latency is also coming in pictures for the replicas to become in sync. So one replica will get the update that it syncs over the network with the other replicas, and when it comes to across the data centers, they will have additional delay. So basically, if a query comes at the same time from 3 different clients sitting in 3 different regions, they might end up seeing 3 different results. But over a period behind the scenes, once replicas actually communicate between each other, they become consistent, and once they are consistent, then they will return back the same result for the queries. So that's the eventual consistency model, which is not consistent immediately, but it becomes consistent over a period or during that over the period. Okay, so that's the base model and not the ACID system. ACID we all know, so I'm not really covering that further. So if you look at, a general thing, right? So again, I'm sure people would be familiar with what we see here. So Panacea is basically a Greek goddess, sort of has solution for everything types. We are absolutely, NoSQL system is not an absolute Panacea. So it doesn't have a solution for everything. Because since of the flexibility that NoSQL systems provide, one of them actually concentrated specifically on one factor, the other concentrated on the other factor. For example, if you look at MongoDB, they concentrated more on consistency and the partition tolerance or the scalability part of it, but they foregone availability. Similarly, if you look at Cassandra, they've foregone consistency at the cost of, the cost of consistency, they got availability and scalability. So since what basically it means is no SQL system will fit every other requirement, that a market can have. So there is a suitability part of it. Some applications where you're talking about this particular thing is more important. Say for example, consistency is more important. Naturally, HBase and Mongo are probably more suitable there. In an application where say time series applications where consistency is not important, Cassandra or CouchDB is more suitable. So approximately about close to 150 different types of NoSQL systems are there out there in the market, and recently I've known that there are even some, I've never heard of something called times 10, which Oracle bought out, and it's become the NoSQL database of Oracle right now. So there are hundreds, 150 of them, but the most popular ones out of these 150 are, if you look at it, I think the most popular ones, rather, let's look at the distribution first, okay. So this NoSQL landscape of 150 databases could be broken down into 4 different categories. What we call it as document data stores, key value databases, NoSQL or columnar databases, or graph databases. And if you look at each of them, they have again specialized properties with respect to the scalability and speed and the query and navigational complexity part of it. So if you look at document database store models, basically where MongoDB, etc. sort of fall into this category. They are basically, again, collections of key values, okay. So if you look at, the weakness-wise of these kind of databases, it's basically the query performance. They're comparatively bad with respect to query performance, and at the same time, they even have issue with the general scalability part of it, because I'm saying they have all the properties, but the weaknesses, basically they don't do absolute great job, is mainly to do with the availability part of it. Because if you look at Mongo, where you have a master slave kind of, sorry. Okay, so this is the document data stored systems. Then the second category is the key value stores, where mostly the data is stored in multidimensional maps with key value stores and etc. So this the categories, the databases which sort of fall into this are Redis, Amazon SimpleDB, etc. sort of fall into the key value data categories, where even Amazon Dynamo actually falls into the same category. It's basically a in-memory lookup of a map kind of thing, key value pairs, right? It is very good for faster lookups, very good at faster lookups, but when it comes to storing no schema, or rather schema-less data, it does have a weakness comparatively, okay, because it's talking about more of, it optimizes on the lookup, whereas it does not optimize on the schema-free kind of a model. Now the third one is basically the columnar databases, where the Cassandra, HBase actually fall there. They have very fast lookups naturally as well as, but very low. They have a couple of problems which Cassandra and other things have. The mechanism, the interaction between them actually is pretty low level API. So you need to be worried about a lot of things, but that's something which is going away with the introduction of SQL and making it a lot more SQL-like support in Cassandra, which sort of 2.0 provides to some extent. So that is what is the columnar database things. Then you have the fourth one, which is the graph databases, where all the Neo4js or the infogrids, infinite graphs, etc., they fall into this category, where the important property of these kind of databases is to do faster searches, graph algorithms, shortest paths, connectedness, etc., which are more interested in searching, in a very fast search capability, but they are not really bothered on the speed or the scalability part of it. Comparatively, they are a little weaker on the speed and scalability side, that is read and write speed side, but when it comes to search, they are pretty fast. Okay, so these are the 4 different types of systems that are available, or rather, a NoSQL landscape could be actually broken down into 4 different pieces. Okay, so we have talked about the compromising features of RDBMS, pros and cons of consistency. Now let's look at how do we choose the right data, and the thing is the right data model. Then these are the important things which you would actually be will help you to make the right choice of whether it comes to the NoSQL systems, right? Say for example, naturally, you come. We've talked about several applications, right? Let's take one more couple of applications just to see if what fits together. Say Twitter, for example. Twitter is one. Actually, okay, let's not rule away this question. Facebook does not use only Cassandra. Facebook uses Cassandra, Neo4j, graph databases. It uses a lot of things, but the purpose of each of them is different. So that's why we always say, choose the right NoSQL system for the right type of application. So if I go and say, for example, I'll take a movie booking application. in a movie booking application or a messenger kind of an application, consistency is of primary importance to me. So if I won't actually choose a NoSQL system where consistency is not a primary thing, but availability and partition are primary things, right? So for those kind of applications, I will choose something where consistency is a primary property which is provided out of the box. So it gives you very more efficiently than the other ones. So that is what you look at when it comes to pros and cons of consistency. So if your application's consistency is the most important requirement, then I would never choose the ones which fall into the AP quadrant, which is availability and partition tolerance quadrant. Okay, then you're talking about again data models. So if your data that you are actually writing in your application is absolutely related to each other, that is, if you have some sort of a student-employee databases. So if your employee ID has to have a foreign key relationship with set of information that is stored across, you can actually denormalize it and store it in an NoSQL database. But if it actually, for example, in the case of financial transactions, say you're looking at financial transactions, where all your transactions have to be consistent and it has to be reliable. You cannot really miss any of the stuff, and security is of primary importance. In all those cases where you would really use the relational database system, you won't preferably use a NoSQL system where these things are primary, because consistency is not really something which is, if it's primary, people don't want to use a NoSQL system, ideally, except for cases where, say for example, movie booking and all, where Mongo is probably used because it gives consistency out of the box, but at the cost of naturally the availability. So there are multiple factors. Let's compare a few of them. Okay, let's understand first the most popular ones which are there and out there, and then I can share some basic investigations, some practical reports on what is good at what point and when you should choose which one for what type of applications. Okay, so let's understand the most popular ones. The most popular ones in the NoSQL world are Cassandra, HBase, and Mongo. Okay, so we're talking about three of them, right? So Cassandra naturally is simple setup, maintenance, and code, because when it comes to maintenance of Cassandra, the administrator has to do nothing. Most of the things are automatically done. So if you want to scale up or scale down, remove a node or add a new node, etc., it's very, very fast in the case of Cassandra, because it provides you a simple tool which can help you to do that. And you don't have to really worry about resyncing, balancing, distribution of data. All these things are actually automatically done. You want to do it manually, you can always do it, and absolutely provides very, very high velocity of random reads and writes compared to the other NoSQL systems because of the columnar storage capability and its distributed decentralized architecture. Okay, flexible sparse wide column requirements, where you're talking about more on capability to increase your columns for a specific type as and when you need. On a need basis, you can alter your schema. It absolutely have no restrictions on that. The only problem, rather I would say it's not a problem, but it is only suitable for a case where secondary index needs are less, which means you have an absolutely denormalized information, which is all information is sitting associated to serve a specific query is sitting in one single table and not goes across multiple tables to get to serve a specific client query. So assuming basically non-group by kind of models. People who are very familiar with RDBMS can understand what a group by means. So non-group by kind of systems, Cassandra is absolutely suitable. But if you have an application which has a requirement of group by kind of functionality, Cassandra is probably not a right system to choose. It supports secondary indexes. It doesn't mean that it doesn't support, but when you are bringing in secondary indexes, its internal overhead becomes so high that the overall performance of the system comes down. The more secondary indexes you use, the less the performance. So you can use Cassandra in those cases where you have less secondary index needs, where you want a very simple setup and maintenance, very high velocity of random reads and writes, and wide column requirements. All these things were sort of very, very well fitted to time series or data where consistency is not very, very important. Okay. An example would be Twitter, where we're talking about very, very massive scale and high availability. A simple thing, imagine the scale of these, right? So if, say for example, Angelina comes out and tweets saying that if anybody who retweets what I've tweeted, I'll have a date with him. assume the number of hits that you will get on the Twitter application. It will be millions and millions of people doing it at the same time. Okay, so it should be able to handle that kind of a scale. And when it comes to availability, naturally, there are millions of people tweeting on millions of topics at the same time. So it has to be available and make sure that people don't have a bad user experience. So where not to use Cassandra? Absolutely no. In the case of a lot of group by second indexes, transactional data, relational data, stringent security and authorization needs, never use it. Okay, and dynamic queries. Since Cassandra is basically the query modeling concept, where you are talking about you model your storage subsystem using queries. So first of all, when you're doing a modeling, you actually look at all the most commonly used queries. Then you model your data. Then you prepare your data model based on that one. Since it's a query-based modeling system, dynamic queries are very, very costly in Cassandra kind of storage subsystems. Okay, wherever there is a dynamic query requirement, don't use Cassandra. I mean, you can use, but you'll get worse performance probably than the other systems. Okay, where to use HBase? It's basically, I mean, pretty optimized to reads, and it is probably one of the best systems used for a MapReduce kind of model, because it was built for such kind of a systems where it was in conjunction with to work well with Hadoop. It was built to work with Hadoop, so it has where applications have good consistency requirements, it could be used, but we're mostly doing range-based scans, because in HBase the database storage is actually done in blocks of data. So your range is much bigger. So if you're range-based scans, you might end up getting it from a single memory block. And the size of the memory block is adjustable. You could actually create this block. It stores data as raw blocks. So that data, as long as your range query falls within that block, it can be just obtained once from one single node. So the distribution is based on blocks. So that's why it's good for range-based scans. Wherever you have range-based queries and all, HBase works really well, and it works really well in cases where you have MapReduce kind of an application, because it was always built with MapReduce in mind. So MapReduce, how it happens is basically you pick up the entire block at one shot and run map or reduce functions on those block of data. So in which case you don't want really to go and search and pick up small data and then run on MapReduce on it. You would rather pick up a huge chunk and run MapReduce, which is much faster and better and more efficient. So Facebook naturally uses it for user statuses, photos, chat messages, etc. The Facebook Messenger actually works on HBase. So where consistency is very, very important, because it gives automatically consistency because of the master-slave model, which it has at the base, and naturally the scale and is available out of the box, because you can just keep on growing by adding a lot of what we call it as the name node and the slave node sort of thing. So they have basically a controller node and worker nodes kind of a thing. So you can actually keep on adding more worker nodes to actually scale it very comfortably. Okay, and then I think Hadoop in this version 2 actually even provides you some capability of adding a cluster of name nodes, and it's not just single, and it's more of active cluster name node concept that's available, which sort of gives you a level of high availability, but it's still a class of servers. So if that class of servers for whatever reason is down, it will create availability issues. Okay, where not to use HBase? Wherever you need full table scans, because it's actually stored in blocks of data, and if the data goes across blocks and etc., which will become really, really painful, and performance-wise it will become bad. So data to be aggregated, rolled up, analyzed across rows, all these kind of cases, you don't really use HBase, because as I said, HBase is right for MapReduce kind of a job, where you have a set of data and you want to run a specific map or a reduce function on those data and just get the results, a lot more independent. So independent pieces of data running each of them separately, but when you have to do aggregation, roll up, analyzed across rows, etc., HBase really performs bad. It's not a suitable system for that. Okay. Now coming to Mongo. Mongo is sort of an RDBMS replacement, exactly what I was saying. So when you have something which is closer to RDBMS kind of requirements for the web applications, Mongo could be another use. Mongo gives you the additional partition tolerance which RDBMS doesn't give, but it has problems with availability, which we talked about, but it still can be managed. So it's sort of an RDBMS replacement. where if you want to have more relational data and you still want to use a more scalable databases, Mongo probably would be the ideal choice. For real-time analytics and high-speed logging, probably it's something which is a suitable system. And then it's also scalable naturally because you could actually comfortably add new Mongo nodes very easily. And you have replicas, etc. Some of the use cases basically would be like Craigslist actually uses MongoDB for storing all the archive posts. Though the current active posts are still in MySQL, but they have migrated about 2 billion plus posts to Mongo. Similarly, Foursquare, where you're talking about venues and check-ins that they have migrated all those stuff from RDBMS to MongoDB. But that's why I said it. For a simple replacement, if you want a NoSQL from the RDBMS world as it is, then Mongo would be the right choice. Okay. Where not to use Mongo? Highly transactional applications where you have, traditional database requirements like foreign key constraints and etc. Because it is still a NoSQL system. It sort of falls into the category of denormalization. So preferably don't use too much of wherever you have too much of foreign key constraints, a lot of joins and etc. Probably it's not a good place. And highly transactional applications. Okay, so this is basically if you look at all three of them. Now in general, if you look at, right, so if you compare sort of thing, right, HBase naturally is distributed and scalable big data store, naturally all of them to some extent, but so comparing wise, strong consistency, HBase, built on top of Hadoop distributed file systems. So very much use HBase in a situation where you're talking about more of MapReduce applications where you have more consistency requirements, very strong consistency requirements like Facebook application, like Facebook messengers basically. HBase is the right one. Now coming to Cassandra, incremental scalability, eventually consistent kind of models, more of time series applications like travel portals, and wherever you, the questions like feeds and etc. you would use Cassandra. Now coming to Mongo is basically again a sort of an absolutely, it gives you a schema-free model, but it's a good replacement for RDBMS. So if you want to replace an RDBMS with an NoSQL system, Mongo probably is the ideal choice to start with. The only problem with Mongo, as I said, is again has issues with all these things really work. So if you look at any of the systems, right, there's a lot of practical data on read and write latencies. So there is a practical experiment which has been done. So if you look at the read and write latencies on these kind of stuff with respect to speeds and etc., Mongo and HBase sort of work well only up to a specific limit of data. Beyond that limit, they sort of degrade in their performance. Say for example, about 32 or 64 GB of data onwards, Mongo and HBase somewhat come down on the performance wise. Cassandra sort of gives a consistent performance beyond that, and even beyond that, when the amount of data increases to petabytes and petabytes of data, Cassandra sort of gives you a very good performance at very, very high volumes of data and high read and write indicators. So that's where Facebook actually uses Cassandra. So where there are situations of writing too much of data into the system and very high volume of reads and writes, and when the scale goes really high, they use Cassandra. For more consistent applications where you're talking about Messenger and etc., they use HBase. And then the other case for Mongo would be more of the movie booking sites or say a replacement of existing RDBMS applications because they sort of fall very close to the mechanism of RDBMS at the base. So MongoDB is more suitable.